Welcome, and thank you for trusting us with your source material. We are diving into a stack of research today focused on really pushing the boundaries of multimodal reasoning in AI.
That's right.
And specifically, we're looking at this core engineering challenge. How do we get language and vision to truly work together, as a single coordinated thought process?
Not just two separate tools running side by side.
Right.
And this deep dive really centers on a technical paper introducing a model called ThinkMorph. It's designed to explore what the researchers call a meaningful interleaved chain of thought.
Okay, so our mission here is to pull out the core insights on how this approach creates a genuinely cross-modal system.
It is. The central idea, and what really makes this research feel different, is the shift in thinking.
Away from what we're used to seeing.
Well, for years, multimodal AI has been, pretty limited to models that just describe images. A textual chain of thought approach can do that.
But that's its limit.
It is. ThinkMorph tries to move towards systems that can genuinely interrogate, manipulate, and even generate visual elements as part of the solution itself.
Almost like how a person might talk through a problem and then grab a piece of paper to sketch something out to confirm their thinking.
That's a perfect analogy. The key principle it's built on is treating text and image thoughts as complementary, not isomorphic.
Okay, complementary, not isomorphic. Let's unpack that because it feels like the foundation of this whole thing.
It is. Isomorphic would mean the text output and the image output are basically saying the same thing, just in different formats.
A redundant description.
And that's why previous approaches fell short, especially on vision-heavy tasks like spatial reasoning. The text wasn't really adding new reasoning, just description.
So to solve a truly visual problem, the model needs to be able to perform a visual act.
Perform a visual act, that's right. A manipulation or a re-rendering that functions as a genuine step in the logical chain.
So how does ThinkMorph actually manage this interleaved thought? How does it switch from, say, verbal logic to a concrete visual action?
The architecture is a unified model, and it was fine-tuned on about 24,000 of these high-quality reasoning traces.
Okay.
And the key is that the model's output isn't just text or just an image. It's a single sequence of tokens. And at any point, the model decides if the next token should be a textual one, a verbal thought.
Or an image one, a visual manipulation.
Correct. It uses special delimiter token, something like image start to signal.
Okay, I'm about to draw something now.
Yes, exactly that. And then it uses image end to close out that visual thought. This creates really explicit boundaries in the process.
The quality of those 24,000 examples must have been critical. Can you give us a sense of the problems it was trained on?
They were built around 4 tasks
Yeah.
that really demand that cross-modal interaction. The first was jigsaw assembly.
Okay, that's obviously very visual. Text alone would struggle there.
It does. Text can describe the shape of piece A and piece B, but it can't really confirm if they fit together in the context of the whole puzzle.
So the text describes the pieces and then the image tokens.
The image tokens visualize the rearranged pieces. It's a physical sanity check to see if the proposed fit actually works.
I see. What was the second task?
Spatial navigation. Basically maze solving. Text is good for a high-level plan, go north, then east.
But terrible for the details, like avoiding a dead end right in front of you.
Right, so the image tokens render the actual path, often highlighting it with, say, a red line or arrows. The model can visually verify its progress step by step.
Okay, and the third was visual search.
Yes. Here, text can guess where an object might be.
Yeah.
It's probably in the top left.
But it can't confirm it.
It can't. The image tokens draw a bounding box around the object to visually anchor the hypothesis and confirm its attributes, to make sure it's the red triangle and not the blue one next to it.
Makes sense. And the last one, chart refocus, sounds a bit more analytical.
It is. The model has to extract data from a dense chart. Text can identify the relevant bar or line.
But getting the exact value off the axis can be tricky.
Very. So the image tokens highlight the specific region, maybe with an overlay, which makes the value extraction much more precise and less prone to error.
In every case, then, the model is trained to know when language hits its limit and a visual action is needed to move forward.
That's the core idea.
So let's pivot to performance. Did this design choice actually pay off? What do the numbers look like?
Oh, the gains are quite large. Across the vision-centric benchmarks, ThinkMorph averaged a 34.74% improvement over its base model.
That's a huge lift.
It is. But for tasks that need that continuous visual feedback, the results are dramatic. We're talking an 85.84% improvement on spatial navigation.
Wow, an 85% jump. That really shows how critical that visual feedback loop is for certain problems.
And a 38.75% increase on the jigsaw assembly task. It confirms that the ability to draw the solution is the missing piece.
Okay, so that brings up a really interesting question from the data. Is interleaved reasoning always the better approach?
And that's where things get more nuanced. The short answer is no.
No.
Overall, interleaving is better by about 5.33% on average. But the need for it really depends on the specific demands of the task.
Tell me about that counterintuitive result from the chart refocus test.
Right, so on the chart QA benchmark, which is the task it was trained on, text-only reasoning actually did slightly better than interleaved reasoning.
Better. By how much?
By 1.88%.
So wait, the model has this new tool, the ability to draw a bounding box to confirm a value, and choosing not to use it made it more accurate.
That's what the data suggests. The inference is that if the initial textual reasoning is clear enough to identify the key elements and get the answer, adding a visual step is just supplementary.
It might even introduce unnecessary noise.
It could. The text-only path was just more direct and efficient in that specific case.
So the smartest move isn't always using every tool, but knowing which tool is the right one for the job.
That seems to be the lesson. And you can contrast that with its performance on an out-of-domain benchmark, MMVP.
Okay.
There, interleaved reasoning generalized much better. It beat text only by 6.33%.
Why have a difference?
Because in those new unseen problems, visual grounding was essential for subtle cues text couldn't capture.
Yeah.
Things like confirming the duck's beak points rightward. Text alone just couldn't solve it.
This leads us right into what I found to be the most fascinating part of this research, the emergent properties. These are behaviors the model wasn't explicitly trained to do.
They just appeared.
What's the first one they observed?
The first is called unseen visual manipulations. When the model was given these out-of-domain tasks, it started generating visual edits that were completely new.
Knew how.
Things like zoom-in operations, in-painting to fill in a missing part of an image, drawing multiple boxes at once, even perspective transformations. None of that was in the original 24,000 training examples.
So the model literally invented new visual tools on the fly. Were they just random, or was there a pattern?
Highly systematic. The researchers found that specific textual cues would reliably trigger these new visual actions.
For example?
A phrase in the text, like examine closely or focus on the detail, would consistently make the model perform a zoom-in operation on that part of the image.
So fine-tuning didn't just teach it a few tricks, it repurposed its raw visual ability into a structured, reasoning-oriented behavior.
It learned how to diagnose its own information gaps and then invent a visual aid to fill them.
That's a major step. What about the second property? They had to do with adaptability, right?
That's autonomous mode switching. Even though it was trained on interleaved data, the model would sometimes decide during inference to just stick with text-only reasoning.
It would just ignore its visual training.
On its own, yes. Particularly on that out-of-domain MMVP benchmark. It happened in about 5.3% of the cases.
And was this a good decision? Did accuracy go up or down when it did that?
It was a very good decision. The accuracy on those specific switched instances was 7.29% higher than if it had been forced to use the interleaved method.
So it knows when to keep things simple. It's making a kind of internal cost-benefit analysis on its own thought process.
It seems to be. It can tell when the initial visual information is good enough, and that text is the most efficient way to get to the finish line.
Incredible. And the third emergent property was about how it handles more complex scenarios.
It's about how it performs under increased sampling. It's called better test time scaling via diversified thoughts.
Okay, let's break that down. You're talking about best of n sampling.
Right. Where you generate, say, 8 different possible solutions or thoughts, and then pick the best one.
And interleaved reasoning scales better when you do this.
Much better. The reasoning is that unimodal chains are stuck in one representational space. A text-only approach will generate 8 pretty similar text-based solutions.
And a visual-only approach will generate 8 similar visual paths.
Correct. But interleaved reasoning generates trajectories that span both modalities. The diversity of the solutions is just fundamentally richer.
Which means you have a better chance of one of them being correct.
And that leads to stable gains. On the very challenging B-length jigsaw benchmark, this gave it a plus 8.0% gain at 8 samples.
And the other method?
The visual-only method actually got worse. Its accuracy dropped by 2.0% on that same test.
So let's zoom out and put this all together. The power of this model, fine-tuned on just 24,000 samples, seems pretty striking compared to the general trend of just building bigger and bigger models.
It does change the conversation a bit. ThinkMorph, a 7B parameter model, is rivaling or even outperforming proprietary systems that are an order of magnitude larger.
Any specific comparisons?
It outperformed the 72 billion parameter Qwen 2.5 VL model on two of those key vision-centric tasks. And it was highly competitive against models like GPT-5 and Gemini 2.5 Flash on reasoning-heavy evaluations.
So the big takeaway here seems to be that the quality and structure of the training data can be a more powerful driver for complex reasoning than just raw computational scale.
That really captures it. Those 24,000 strategic samples were enough to teach the model how to think adaptively.
It created this self-reinforcing loop where the act of generating a visual, the manipulation, actually strengthens its understanding.
The generative process directly enhances comprehension. That's the core finding.
Before we wrap up this deep dive, we've really seen how ThinkMorph internalized these adaptive strategies. It's not just following instructions, it's recognizing when a certain tool is necessary and even inventing new ones when it gets stuck.
Which leads to a final provocative thought for you to consider.
Okay.
If a system can autonomously decide its most efficient mode of reasoning, switching between abstract symbols and concrete perception, and can spontaneously invent the visual tools it needs to bridge those gaps, what new definition do we need for internalized problem-solving strategies in artificial intelligence?